Welcome everyone to session D421, Requirements and Challenges in Developing Complex Systems. The theme of this session is indeed complexity. It's both about requirements and concept and architecture and setup, as well as challenges and kind of some of the system engineering challenges. We have 5 interesting papers being presented, and the 5 presenters are all here. You see on the video the sequence. The way this will work is we'll play all 5 of the pre-recorded presentations, and during each presentation, we'd like you to click on the tab for chat and enter some questions or comments for each of the speakers, and start it by naming the speaker or the paper number 1 through 5 or the speaker's name. And you probably know if you use the @ sign, start typing the first few letters of the speaker's name or another commenter's name, and then you get a pull down menu of their names, and it'll tag them in the chat. If you don't know about that, don't worry about it. It's going to work fine. So I think we're ready to start, and I'll ask Robert, our professional moderator, to run the videos for us. So please, Robert.
Hi, I want to talk about automated requirement dependency analysis for complex technical systems. My name is Oleff. I'm from the chair of product creation. Our head is Professor Gräßler, and we belong to the Heinz-Nixdorf Institute and University Paderborn in Germany. We are currently looking at the following context and problem. So developing complex technical systems usually goes along with interdisciplinary and extensive requirement sets. And many studies for many years show that the insufficient management of requirement changes is one of the major reasons for project failures. We wanted to tackle this issue and found that the change propagation is crucial. So we need to be better at estimating propagation effects to make better decisions about changes in the future. And to estimate such propagation effects, we need dependencies. We need dependency analysis. So we looked at existing approaches, and we found that they have one or more shortcomings in the following 4 areas. First, they are not able to assess or process large data sets like 100 or thousands of requirements. For example, manual approaches are usually not suitable for so much data. They sometimes rely on historical data, which is not broadly available in companies because it's very specific. You need to know which change had what propagation effect. So this is not broadly applicable. The third is that we need to be better on the content side, on the precision as well, and therefore we need to differentiate dependencies by propagation behavior and need to look at higher order dependencies as well. And to tackle this issue, we followed a 4-step approach. First, we did a literature review on which solution classes we can consider. And we found, which was previously published in other papers, that machine learning is, for example, better suitable than ontology-based approaches. So we picked machine learning and tried to figure out which approach is best for us. And so we defined some performance indicators like recall, precision, and so on. We created some case study data. We implemented 4 approaches, and we found that one of them, called BERT, which is a very novel transformer-based machine learning, is most promising. So we used the BERT approach to develop something new, the Advanced Requirement Dependency Analysis, which consists of a method and a software prototype. And the 4th step is to evaluate our results. So we looked at 5 case studies, for example, a robot, and we made 3 workshops with industry experts to assess, for example, application effort. And the method we created is follows these 3 steps. First, we need to select a pre-trained model. Those are usually open source models for the BERT approach and can be just taken from the internet, from Google, for example, or Hugging Face. And those are special because they find content-based relations, not just semantically similar requirements, but contently connected requirements. And then you apply a supervised fine-tuning. So you label some context-specific data, and you fine-tune your parameters, and then you have an actually working dependency engine. And this you can use and apply, and it's fully automated. It starts with the pre-processing step. Then there is a classification layer to define the dependencies, and then you can export it towards Excel or IBM DOS, for example. And we found that we have whole new possibilities due to this approach. Compared to a manual approach, which is usually limited to requirement sets with about 30 requirements, we can now look at whole systems with more than 1,000 requirements because we have it fully automated, and we can have a whole new perspective over disciplines and make way more or way better estimates on change propagation. And the evaluation confirms this new possibilities are not just there from the performance side, like processing time-wise, but also in terms of accuracy. So we found that the application effort is good because it's mostly automated. We have all the required information available because we just need the requirement descriptions. We have sufficient comprehensibility. We have good processing times. For example, you need just about 15 to 60 minutes for 1,000 requirements if you use a Google Cloud server. And we also have good performance. There is some limitation, so the performance is, as always, for machine learning, only good if you have a suitable data set. And this is also the most important future work. So we need to find ways to generate the training data more efficiently. So far, we did this fine-tuning labeling manually, but there are approaches on synthetic data generation that need to be looked at in the future. And that's it. So thank you everybody for listening. We hope you find interest in our topic, and please feel free to contact us and ask questions.
Okay, thank you, Christian. And let me just remind everyone, please type a few questions or comments for Christian into the chat. I've got a few. I'll try to type them. I've got to paste them in, and others can do the same. All right. The next paper is from Adelia Drego, and she's at Saab. Okay, please run this presentation. Thank you.
Welcome to my presentation on harnessing the complexity for vehicle system design at the concept phase of an aircraft. Vehicle systems enable an aircraft to fly safely throughout a mission. Typically, they are the systems that transfer energy to other systems, equipment, and subassemblies in the aircraft. Generally, vehicle systems that are common to most types of engine-powered aircraft include the environmental control system, fuel system, electrical power system, actuation system, and landing and braking system. If the life cycle of an aircraft was defined by ISO standard 15288, then vehicle system design would typically commence at the aircraft development stage, then at the aircraft concept stage. This paper proposes that vehicle system design commence at the aircraft concept stage because function, performance, weight, and volume of a vehicle system impact those of an aircraft. Aircraft are complex systems, and vehicle systems have to be integrated into them. Therefore, for a vehicle system to be feasible for integration into an aircraft, it cannot be designed in isolation. Vehicle systems may have connections to several other subsystems in the aircraft. In addition, vehicle systems are usually closely spaced to other subsystems and equipment in fighter aircraft that may affect their function and performance. Therefore, all dependencies and interactions with other subsystems and equipment must be accounted for. However, these important aspects may not be defined at the aircraft concept stage, making it difficult to generate feasible vehicle system concepts. A framework for harnessing the complexities for vehicle system design at the aircraft concept stage is proposed in this paper. Aspects from axiomatic design theory, design structure matrix method, feature modeling method, and the system thinking approach are employed in this framework. The framework is described with a case study of an environmental control system, or ECS, of a manned fighter aircraft. The first step in the framework is to define system attributes in the stakeholder domain. The system attributes for an ECS of a manned fighter aircraft are distinguished between those that are flight critical from those that are mission critical. With system attributes defined, the second step is to define the ECS boundary and subsystems and equipment at the boundary. The upstream systems are the systems that the ECS may depend on. The downstream systems are the systems that may depend on the ECS. For example, the ECS may need electrical power and bleed air from the engine to run, while the ECS itself may provide pressurized air to multiple consumers from the cockpit to the fuel tanks. To assist a vehicle system designer translate system attributes to functional requirements, the main aspects of a vehicle system are identified using a feature model. The ECS has four main features: refrigeration, heat exchanging, air supply, and heat transportation, each of which have various alternatives. With a feature map in hand, system attributes can be translated into functional requirements. System attribute SA1, pilot comfort and safety, for example, can be broken down into three functional requirements: FR1, FR2, and FR3 for the ECS case at hand. That is, providing conditioned air to the oxygen generating system, pilot anti-G suit, and pilot air ventilated garment suit, respectively. For the ECS case at hand, all flight critical attributes are translated into pneumatic requirements, and all mission critical attributes are translated into non-pneumatic requirements, as shown in functional domain 1. Then all pneumatic requirements are lumped into a single functional requirement FR1 that is defined in functional domain 2. Similarly, all non-pneumatic requirements are lumped into a single functional requirement FR2 that is also defined in functional domain 2. Before functional requirements are mapped to design parameters, the input constraints for a vehicle system must be noted. Input constraints could include weight, volume, cost, safety, and reliability. For an ECS, they could also include minimum mass flow rate, temperature, and pressure for air provided by the ECS to keep the pilot comfortable during all phases of a mission. With input constraints listed and with the help of the feature model created from step 3, functional requirements can be mapped to design parameters. For example, FR 1.1 cool bleed air is mapped to design parameter DP 1.1 heat exchanger. The physical domain here represents an ECS concept for a manned fighter aircraft. The design matrix created after mapping FRs to DPs should be analyzed to determine if the ECS concept is functionally independent. The design matrix can then be used to generate the architecture of the ECS concept. An architecture in this paper is defined as a pictorial representation of the relationships between design parameters and operands, the operand being the thing the function changes. For the ECS concept at hand, it would be air and polyalpha olefin. The final step in the framework entails a hazard analysis of the vehicle system concept. First, all the subsystems the ECS will depend on, the components of the ECS itself, and the subsystems that will depend on the ECS are listed as shown on the left-hand side of the screen. Then, the list is used to create a component design structure matrix as shown on the right-hand side of the screen. The DSM can be used to identify redundancies for the ECS itself or for the systems that depend on the ECS. To address the complexities of vehicle system design at the aircraft concept phase, an 8-step framework is presented. The framework may be extended to include techniques to predict emergent behavior of a vehicle system. Thank you.
Great, thank you,
Good morning,
Adelia.
good afternoon.
Okay, next paper is being presented by George on requirements trade-off considerations. And let me just remind everyone to type some comments for Adelia's paper, the number 2 paper, into the chat. I'm going to do one right now. And then, yeah, we can play the 3rd presentation. Go ahead.
The title of our paper is Requirements Trade-off Considerations in Design Evolution, and it is co-authored by Chuck Kirschman, David Gorsich from the U.S. Army Futures Command, and Nafiseh Masoudi. Both Chuck and Nafiseh used to be my students. This paper is motivated by the need to evolve designs considering user requirements. Engineering designers capture requirements using various approaches and then consider them as individual objectives or criteria and may combine them into some super objective. Then they will have to trade off between them. Often this is a catalog design exercise, what solution to implement to achieve some improvement in specific objectives at some variation in cost or other criteria. Innovations drive this process since customers always want better and often newer designs. Note that most of the time, the basic function of the artifact may not change. For instance, a car takes you from point A to point B, but the various additions, improvement in functions, affordances, or looks change, enticing the customer. See, for instance, car advertisements. They rarely mention the main function, which is to take you from point A to point B, but they may focus on what may differentiate their products. So our research question is the following. Could some graphical method help the engineering designer in the trade-off decision process? Here are example graphical methods. The first is an illustration of a 2-objective, 2-variable optimization problem on the left-hand side. In the design space, the allowable domain is illustrated in yellow, limited by the constraints. In the objective space, the middle figure, the trade-off between the 2 objectives is visible on the Pareto curve, which is the bottom curve on the figure. This approach obviously is limited by the number of objectives and variables, because visualizing more than 2 objectives becomes very difficult, if not impossible. The star diagram on the right-hand side allows the designer to compare solutions by specifying the objectives or criteria magnitude for each design. The value of the design solution could be related to the surface defined by these magnitudes. The issue here is the scale of these objectives, which would be very different, but could be normalized. Ouellet in 1992 looked at design criteria for a vehicle and combined several objectives into 3 metrics. Please, which is related to looks, performance, usability, protect, related to safety, and I cost, which is the inverse of cost, so that a decrease in cost is desirable. The current solution is at the middle of the 3 axes, and any improvement is to move away from that point and do some trade-off. Interestingly, asking users if they want a please vehicle without considering cost or protection, they typically identify a sleek vehicle such as a Ferrari or a Porsche. If they only care about cost, then the smallest, cheapest vehicle is selected. If protection is most important, then either Volvo, BMW, Audi, or a very heavy Hummer or tank is selected. The Army published the following iron triangle to show how Army vehicles evolved in the past 30 years, from the Humvee to the MRAP to the JLTV. The three metrics considered are performance, protection, and payload. Comparing these three vehicles, we see that protection was the main criterion addressed, but had some trade-off in mobility between the Humvee and the MRAP. And the next iteration produced the JLTV, which still had significant better protection than the Humvee, but slightly less than the MRAP, however, much better mobility than the latter. The Humvee itself evolved over the years, addressing mobility, payload, and standardization. These are some of the variants of that vehicle, not all of them, but they show the progression. Displaying this evolution on a star diagram, we see that all criteria were progressively addressed and improved. What is not shown is the cost aspect of these changes. Now, to improve any criterion, effort has to be expanded. Effort is manpower, cost, time, and it is usually an increasing function, probably parabolic or exponential, since little improvement requires little effort and more improvement requires much more effort. Superimposing effort over the three metrics of Ouellette, we generate some design ball. Note that the effort would be different for each criterion, so the ball really would not look as perfect as this is shown in here, but this also could be implemented on top of a regular star diagram with multiple criteria. What can we infer from the design ball? The width of the ball may be related to technology flexibility. A flat ball has much room for improvement, a narrow ball requires much effort to improve. Now, a similar ball could be created also for the three metrics of the Army vehicle, if we had any idea of how much effort it would take to improve on each one of those criteria. Also, it may be necessary to jump to a new technology and have a new ball. For instance, going from a fuel-based vehicle to hydrogen-based vehicle would be a technology jump, and then you would have a different ball. In conclusion, if companies are able to create such graphical approaches to their designs, they may be providing their designers with a valuable tool to help them make decisions, trade-off decisions. Unfortunately, generating such data has to be done within industry to assess its potential. So we challenge industry to consider this and identify the potential and weaknesses of this approach. Thank you for your attention.
Okay, thank you, George. I appreciate that presentation. I'll type a comment into the chat for you as well, and I hope others will do the same. Okay, the next presentation by Carl Toller is coming up next. Here we go.
The main purpose of a designer is to maximize the value of a product, service, or system. This clause, however, is not as simple as it might sound, since the construct of value is often complex and multifaceted. This was the main idea going into a qualitative single case study that formed the paper named Issues in Capturing and Utilizing Non-Functional Requirements Along the Road to Servitization, written by me, Carl Toller, Christian Johansson, and Marco Bertoni, all from Blekinge Institute of Technology. Starting with a short background. Non-functional requirements increase in importance when servitizing. This is due to that the functional aspect and the purpose is still connected to the product. However, manufacturing firms have a tradition of mainly focusing on the delivery of the functional requirements and not so much in actually capturing and utilizing the non-functional aspects. Previous research has also to a high extent focused on the market perspective, while we in this paper have decided to take a designer's perspective. But before we go deeper into this case study, we'd like to share a definition of value that's been used in this paper. And that is that value can be seen as the degree of fulfillment of needs with respect to all system constraints, which is then measured in terms of functional and non-functional requirements compared to inclined cost. Breaking this statement down, we can see that the value is mainly the fulfillment of needs compared to the inclined cost. However, needs are often hard to quantify as they are informal and naturally expressed. So therefore, they need to be translated into something measurable. And this is functional and non-functional requirements, where the functional requirements correlate to the purpose of the system and the non-functional requirements to the qualities of the system. This, as I said previously, was a single case study, a qualitative single case study done at a manufacturing firm at the start of its servitization journey. So the method was firstly to conduct a data collection in the form of interviews and observation. This formed a case database. This database was then refined and important information were extracted and validated with the participants to ensure there was no misunderstandings along the process of extraction. So this list of findings were then consolidated and categorized and ultimately led to a list of issues, which is presented in the results here. So we can see that we're able to identify a total of 6 different issues that were mapped along the product development stages in the process according to Ulrich and Eppinger. We can also here see on a higher level that the majority of the influence or on the early stages, which is reasonable as the majority of the elicitation takes part in these stages. Looking a little bit more into detail of each step, and see the first one is that need translation is incomplete. This means that not all needs were translated, especially in the non-functional requirements domain. The documentation of this translation was also missing, making it harder to backtrack later on. The needs that were actually translated to non-functional requirements were mainly of a must-be style, if you look into the Kano characteristics, while one-dimensional performance aspect or attractive requirements were not included. We also found that R&D were not participating in elicitations to any larger or significant extent. This was done only by the marketing, which causes a risk of missing perspective and also increases the distance between the source of the need and the realization of it. Further, there was found to be an over-reliance on ethnographical methods for elicitation, and as these were deemed to be very cumbersome and time-consuming, they were done more ad hoc, and they were also viewed as being relevant for a very long time, which can be questionable. At the same time, the case company have deployed operational data collection that could be used in elicitation, but it was not used to any significant extent. Further, the requirements verification was very limited, and the verification was done only in the functional requirements domain. Non-functional requirements were often without any clear measurements or evaluation criteria, ultimately causing a skewness to only focus on fulfillment on the functional aspects. There was also no clear process and support structure for how to work with non-functional aspect in the development process and elicitation process. The employees experienced that they had a lack of tools for converting the more fussier needs into requirements, which are typically the ones that are correlated to the non-functional. Finally, there was a highest performance to lowest cost culture, favoring the functional requirements even further. So the conclusions from this qualitative case study was that firstly, non-functional requirements are crucial for servitizing manufacturing firms, but they are hard to work with and have found difficulties in using this in the traditional processes. At the core, it was found to be a lack of support for dealing with this non-functional requirements and translating the needs without losing the rationale. That was one of the main issues. So looking forward, we can see that there is a need to do further studies, partly to verify that this was not an isolated case, and also to identify different tools, methods, and support that can be deployed to improve the situation. With that, I would like to say thank you and open up for questions and discussions.
Thank you, Carl. Very good. Please, everyone, type a few questions or comments for Carl to address when we get to our discussion. Okay, I'm looking forward to the final presentation. It's by Yevgeny Palyenko in Stuttgart. Here we go.
Hello, ladies and gentlemen. It is a pleasure to welcome you to the presentation of our paper. My name is Yevgeny Palyenko, and I work at the Institute for Engineering Design and Industrial Design at the University of Stuttgart. In the next couple of minutes, I will talk about a paper that is titled Inquiry and Analysis of Challenges in the Development of Smart Product Service Systems. First of all, let us start with a brief introduction into the topic and the underlying motivation. In the past years, a shift in the economic landscape can be observed. Increasing competitive pressure and shifting customer needs force enterprises to change the way they conduct their business and change their business models. Especially producing enterprises often try to improve their value proposition by providing additional services, thus satisfying their customer needs through so-called product service systems. Such systems can be either classic or smart. While a smart product service system bundles tangible smart products with non-tangible data-based services. Typical examples for such systems are predictive maintenance or process optimization. Overall, smart product service systems are complex systems that require specific knowledge and skill sets for their development. Thus, enterprises, especially small and medium-sized ones, struggle to develop successfully smart PSS. In order to support those enterprises, different methods and frameworks have been already developed, and they are generally applicable. However, they require reconsideration and adaptation for the development of smart product service systems. One of the main reasons for this is a lack of industrial viewpoint in the development of those support measures. And thus the existing support does not quite fit the real needs of the enterprises. Therefore, our research focuses mainly on the following two research questions. Firstly, what are the challenges faced by German SMEs in developing smart product service systems? And secondly, what support do German SMEs want for the development of smart PSS? In order to address those research questions, we have conducted an explorative multi-method study, which consists of a written questionnaire and in-depth interviews. Overall, we managed to acquire 18 participants from 5 different SMEs, which differed in size, sector, and line of business. And those 18 participants had the roles of being IoT developers, chief technical officers, service managers, product managers, and many others as well. Now, let's take a closer look at the study design. First of all, we started with a broad literature review that allowed us to prepare the questionnaire script and glossary, all of which underwent multiple reviews, revisions, and trials. Then we were able to issue the glossary and provide the glossary to the participant in order to create a common understanding of the topic itself and provide definitions of basic terminology. Then we issued the questionnaire and conducted the interviews, following with a result analysis and review of the findings. In accordance to our research questions, our findings can be split up in two sections. First, the challenges in the development of smart PSS, and secondly, the areas for requested support. Overall, we are able to identify 27 challenges in developing smart PSS. But let's take a closer look to the main set of challenges. The most patients received the development of suitable business models and the lack of know-how regarding the development of smart PSS. Following data information know-how management during the development, as well as capturing customer requirements and integrating customers and product users into the development. The second section of our findings are the areas for requested support for the development of smart PSS, which we were able to identify 20 different areas. Whereas the two main areas with the most mentions are the integration of product and service development, customer and product user integration into the development process, development of data-based services, and the integration of smart components into new and existing products, as well as establishing new business models for smart PSS. Now, to conclude our findings, we were able to discover a broad variety of challenges and areas of requested support for the development of smart product service systems. Therefore, we can provide a profound basis for future research on methods and frameworks for the development of smart PSS. In our opinion, the most important findings of our study are that the current development process at German SMEs seems to be inadequate for the systematic development of smart product service systems, and that the integration of product and service development processes appears to be a problem. Therefore, further investigation and research regarding those two topics is necessary. Last but not least, we would like to thank our research partners and participants of our study that were from the Research Alliance Be Smart, and of course the financial support by the Federal Ministry of Education and Research of Germany. For further information on our research and the study, feel free to visit us on our homepage of Be Smart. And of course, this is the literature that we have referred to during this presentation. Before finishing our presentation, we want to thank you for your attention. If you have any questions or remarks, feel free to voice them.
Okay, thank you, Yevgeny. And I'd like to thank all the speakers today for pre-recording your presentations. That allows us to keep this perfectly on time. And now we should have about 30, maybe 35 minutes for some discussion. Unlike many of the sessions in this conference, there's a pretty strong theme here related to complexity. So I hope that we'll have some, in addition to one-on-one discussion with individual presenters, maybe some discussion across. I think some of the papers address problems that relate to those in other papers here. So we should have some interesting discussion. So I hope everyone has taken the opportunity to type some comments. It's not too late to add more, so I will try to find the comments for each presenter. And in the case that I don't think, or the presenter doesn't think the question is clear, we'll ask you to clarify. We'll ask you to unmute and voice them if necessary. Okay, so I'll start with some comments for Christian, who presented the first paper on the dependency analysis. So Christian, I hope you're ready for some questions. Let me start with the one that I typed in at first around prediction versus probability. So you're looking at propagation of changes, and I'm wondering if the type of data you're using, since it's so much richer than we normally use in change propagation methods, is it better able to predict changes rather than merely identifying that because there's a relationship, there's a possibility or a probability of change. So I wonder if you can address that, which is the first part of my question first.
Okay, so thank you for your question. That I think that's a very important point. What we did in this research is we tried to differentiate certain types of dependencies. So we investigated if there is mandatory propagation in some cases. So, for example, if there is a requires or refines and the other direction is required by, we investigated this on how we can derive a certain propagation probability from this. And the approach is able to differentiate such dependency types. So still we make a probability estimate, but it's more precise than just a binary or network-based probability analysis where you just count the number of dependencies coming in or going out. So based on this characterization, we are able to make more precise estimates on the change probability. Some more details on this. So we are this is part of a bigger research, and we look into this likelihood or probability estimate in more depth in a future paper, because you also need to consider those. Like this is only the propagation probability, and to estimate the change likelihood or the change probability, you also need to look at the external triggers and match those. And this is quite difficult, but we think we have a solution which will be published in a follow-up paper.
Okay, I think I'd just like to double click a little bit further on that. So I understand there's a difference between A is connected to B, or A provides some data to B, or A provides torque, or A provides voltage. I'm like, there's a relationship, but that doesn't mean that if you change A, that B needs to change, or that if you change B, that A needs to change. So I understand the difference between there's a connection, therefore there's a possibility of change, rather than a likelihood or a probability. How do you differentiate that?
Well, that's an unsolved issue. We just can try to get as close as we can. So what we would need is a big empirical database. This is not existing as far as I know. So we made case studies and looked at those case studies. And if you look at the hierarchy of requirements, from our perspective, there are mandatory change propagation effects. So if you have a higher order requirement, which is refined by further requirements, if there is a change in a detailed requirement, this needs to follow up the path upwards. But most of the time, it's not mandatory. So it's just a probability we can estimate. And we made some case studies, we made some assumptions, and then we compared them to the reality, basically, and saw that it's not perfect, but it's better than just a binary approach.
Okay. Thank you. Let me turn to Khadijah's question that you may see in the chat. And you may have partly answered this already, so let's just read it and see if you can elaborate any. You mentioned that the approach you've used has been better than the ontological approach. Can you please explain that a bit more, and what consideration was taken in that comparison?
Yeah, so more details, you can find the references in the paper. I just showed them real quick in the presentation. We did a previous investigation on the comparison of different approaches for dependency analysis. And basically what we did is we talked to industry experts and defined some criteria for comparison, for example, application effort, but also if they enable to differentiate such dependency based on propagation behavior. And also, which is important for the ontology-based approaches, is the required knowledge available in early stages. So since the cost of change are increasing, you try to perform dependency analysis and like proactive management of changes in the very early stages of development. And usually experts have not sufficient knowledge to create somehow complete ontologies. So that's the major disadvantage we found, especially if there is high novelty in the products. And this is why we chose a machine learning approach. Still, I would say ontology is it was a close call, to say so. And in my opinion, ontology and machine learning are a very promising combination. Which we are currently doing research on.
Yeah, in addition, of course, use of expertise,
yes.
Human expert plus the machine learning. Okay, so my last question, there's a difference. It's really about where's the data coming from. So we're talking about, as you pointed out, I think in your presentation, you said this. We're not talking about 30 requirements. We're talking about 1,000. And so for 30 requirements, you can ask people, how does this relate to this? 30 by 30 is hundreds of things, but it's not too many for experts to answer or consider. But thousands, now you have, potentially hundreds of thousands of connections. So that's too many to ask experts about. So where do the data come from? Do you just extract CAD data? Well, that's one possibility. How do you train the machine learning with sufficient data to be able to analyze here?
Okay, so there are two steps that need to be differentiated. The first one is we used a generic model, which is open source available from Hugging Face, which is a pre-trained machine learning dependency engine based on Wikipedia and text corpora. So what they did is they tried to find content related words like material and steel, which are very often linked to each other. And since it is an enormous big database, results are decent. And what you do in a second step is to do a context-specific refinement. So for the actual task of dependency analysis. The data we used for this was created manually. So we created ground truth data by labeling, I don't know, it was about 80 requirements in a DSM. And so this was quite an effort. But maybe there the ontology can help to reduce the amount of data we need. And then we also use some basic techniques of data augmentation to enrich the data set. But we did not analyze CAD or cut data. In my opinion, this would be promising for a supervised approach, which, like cut is one example where we can find such ground truth data from.
Right, especially with the newest CAD systems where you can actually get the code, you can extract the code, you can extract the dependencies. I haven't seen that done at scale just yet, but it's promising and it's clear that that's coming. Yeah. Okay, great.
Yes, thank you.
Thank you, Christian. Okay, I think I'd like to turn to Adelia. There's several questions for Adelia in the chat. I'm going to start with mine since I think it's a kind of a higher level question, and then I'll get to George's question and a couple of the others next. My first question is, you said that the interfaces are not sufficiently designed in the concept and the kind of system architecture stages. And I just want you to clarify why not. And my conjecture is it's a matter of, well, we've only defined it at the highest kind of system functional level, but not 2 or 3 levels of decomposition down where many of the interfaces lie. So is it just a matter of we haven't gone to those lower stages yet? That is, we haven't detailed them out, or is it a matter of we've identified only the fundamental interaction? This has to work with this in order to make it function properly, but not the sort of what we call the incidental ones, like, well, this one creates heat, and this other thing is sensitive to heat, so there's a bad there's an incidental interaction. We didn't plan for it, or it's not creating its function, but it's harming its function. And if we don't really get to that till later. So I'm just wondering, essentially, why not?
Yeah, thanks, Stephen. That's a really, really good question. Actually, it's more of the latter, because firstly, first I must say that prior to creating this framework, I did a bit of an empirical study at Saab, qualitatively trying to look at the processes in the concept stage. And I noticed, at least from the last 20 years, with vehicle systems specifically, there's been a lot of legacy data. So they tend to use that and to sort of create just initial system layouts. And when I say system layout, I mean literally just the power flow, like creating an architecture of saying, here's the hydraulic system, here's the ECS, here's the electrical power. And then later on down in the concept stage, you figure out, oh, wait, the tactical budget wasn't quite right. We'll have another radar that might require more power or cooling. So it's that sort of, if you call it decomposition. And then there's the next one, which comes in later, where I think it's because it's the influence of who says what when it comes to placing the systems. For example, okay, we're going to place this here, and oh no, there might be its performance might get affected by another system sitting close to it because of thermal emissions or other. So it's a mix of both. It's decomposition and how the current processor working, and then the involvement of different people, and when they should be brought in to the concept stage.
That's really interesting. It just seems to me that, well, it's relatively easy for designers, systems engineers, and architects to think about these fundamental performance requirements. It's harder to think about these incidental ones, partly, as you say, because, well, it may depend on exactly how you package it. If you position it here, there's some interference. If you position it there, it's not. We don't know yet because we haven't done that yet. And one thing that I've found helpful when we do try to put these what we call incidental interfaces into DSM models is to identify the types of incidental interfaces that matter. So when you think about it, it's essentially various types of interference. So there are thermal interferences, there are vibrational ones, there are electrical, like radio frequency and kind of RF interference, kind of electrical, or electromagnetic ones, I guess you'd call it. There are, and there's just a few others that come to mind, that like power management and things like that. And of course, for different types of systems, maybe only certain types of interferences are relevant. And for other types of systems, like if you were designing a smartphone, you'd have a different set of interferences you'd worry about than if you're designing an aircraft, right? But so that if you can specifically ask about those issues, it could be that they're it's actually possible to identify those potential concerns even at the concept and system architecture stage. I wonder if that approach, you think that has any promise in your types of systems?
You mean using the sort of DSM that you just described?
No, not necessarily using DSM. What I mean is, instead of just asking, what are all the requirements or what are all the concerns or issues, you go a level down and say, where are all the RF interference issues going to be, and where might they be, and where could they be? And then people think specifically in that one domain. And then you say, okay, now where's all the vibration issues going to come up? And where's all the power management issues going to come up, or whatever it is, and you think about those specific domains of these types of interferences, not just requirements. Maybe they're going to be more feasibly identified in those early concept stages.
Yeah, that's actually really interesting, because I'm currently doing that. It's a follow-up of what I've presented here, that I'm actually looking into emergent function and emergent performance by looking at it from 4 levels. So if you have a vehicle system concept, you start at the operational level, where you're deciding the operational concept design, how we want to fly the aircraft, what type of missions, etc. So and then the next level, at the aircraft level, what modes do we want, as in modes, as in how, what kind of function, how does the aircraft perform a function? Like a mode could be takeoff, a mode could be on ground using auxiliary power. And from that level, looking at each, so saying, okay, here's this ECS, what functions of at the aircraft level will interact with its functions, and then the same for performance from both physical systems just sitting in its vicinity to literally its physical interfaces that it both its consumers and its providers, and then as well its operational envelope. So I've actually my next step in my research actually is doing exactly that, looking at emergent function, performance, safety, and behavior from different levels of design in an aircraft project.
Got it. So there's a lot of expertise that can help develop these answers if you ask the right questions. And if you don't ask the right questions, maybe that expertise won't develop those answers. And there you go.
Yeah, it's because we have integrated product teams, but I'm looking more into the effectiveness of an integrated product team. How can they work more effectively to predict these issues in time?
Okay. Can you turn to George's question around spatial constraints? So this specifically says you mentioned different constraints. You didn't say anything specific about spatial ones. And how do you, is it possible you'd find a solution that doesn't fit into the appropriate package or space? And how do you think about that?
I think I didn't mention it while I was presenting the pre-recorded presentation, but I did in the paper. But the interesting thing with volume, it's really important for a compact fighter aircraft. And I can't speak for all other aircraft developers, but maybe this is a cultural thing in Sweden. What I've seen is that if you have an issue with volume and you say, okay, this is the power density of the system, but we need a little bit more, but it'll occupy a little bit more volume, then it really is a compromise. I think that, because then you'd say, okay, either we go for the slightly smaller system, and then in this phase of flight, we can turn this off and this off, and it'll be okay. We'll still be able to return to base. The pilot will be safe, and it performs its mission requirements that it's supposed to. So it comes down to a compromise, I would say.
Okay.
Can I add something to this?
Yeah. Go ahead, George. I was going to just give your other question around axiomatic design, but if you have a better...
Yeah. Well, I think Adelia addressed some of my question by answering yours, but some of the things that I keep wondering, a lot of, for instance, the different types of requirements that may appear will not appear until you have solutions, until you have an implementation. Can you say, okay, this is too close to this because of that? But if you don't have that solution yet, how can you tell who are you going to involve? How can you tell, I need to bring the people from electromagnetic because eventually it's going to be too close?
I would say it's flexible, George. It would change as time goes by, because like you said, like if there's some equipment that needs a Faraday cage, then at that point you would involve the right person at that point. But I can't really say how it's but it would go in a way that it's as the requirements change, as new solutions come in and you're integrating them, then I think you involve the people that need to be.
Okay, great.
Thank you.
All right, let's turn to George. There are a few. Thank you, Adelia. I appreciate your paper very much.
Thank you.
Okay, let me scroll back to the questions for George. Okay, yeah. So about I'm going to call it the trade-off bowl. About the trade-off bowl. I'm just struggling with the multidimensionality here. Iron Triangle's got explicitly three dimensions, but in principle, even any one of those dimensions, let's just call it performance, could have multiple dimensions of performance, or even cost. It could have operations costs, it could have production costs, it could have development costs. So, I mean, 3 is a pretty minimal way to think about, you know, the iron triangle. Is really, it's a whole spider or a star or whatever. So how do you deal with the multidimensionality of this?
Yeah, I agree. And I mean, I did mention that it may be possible to take a star diagram and try to think about implementing this effort on top of it, and then have each axis basically have a different curvature. But it would be very difficult to make and to understand what happens. But what was interesting for me, I mean, I worked with GM, and the first work that Oleff did was with General Motors, and they wanted to bring it back down to about 3 performance indicators.
Mhm.
And what those 3 R's is pretty generic. And it was interesting also to see that the Army looked at 3 basic requirements. I think the main issue that we were trying to deal with, all the approaches that we were looking at were applied to designs that already existed, and they were trying to figure out, okay, how can I improve protection for an Army vehicle, and what are the issues with that? I mean, there's different levels of protection, obviously, but if you just come and put a huge Kevlar coating or whatever it is, the weight changes, the mobility changes, so it affects other things. So they were trying to figure out, okay, can I tell what would be a good solution to try to address more or less at the conceptual stage of evolving a vehicle from one version to the next version. And I don't know. That's what we came up with, but definitely it does have limitations.
Okay. Yeah, I mean, the multidimensionality is part of the issue, and you know, the iron triangle. I mean, it's a matter of combining a few of them into one dimension,
Right.
which kind of relates to, I guess, Carl's question. Normalizing requirements enables better comparison, but if fulfillment of requirement are not linear in relation to customer satisfaction, how do you visualize that? Or do you just have to look at this as a trade-off in the requirements domain?
Yeah, I was trying to understand what do you mean, Carl, by fulfillment of a requirement is not linear with the relation to customer satisfaction. So you're thinking that a customer, I mean, we've got the requirements, and one requirement is a lot more important than the other one. And
no, I think the nonlinearity is different. It's saying if you give them a little bit more of this performance dimension, that's helpful. But until it gets to that level, it's not good enough for, you know, the mission. And above that, it's not helpful. So you have a nonlinearity in the amount you fulfill it. There's a nonlinearity in the value to the customer, even on any one dimension.
Yeah, say to we just even there. So it's looking at the Kano model, for instance, like how will where is 0 and 1 in the normalization, and how much is if you take the engine power, for instance, what is 0, what is 1, how much is that in customer satisfaction, so to say, and how do you visualize those aspects?
Yeah. Well, we were what we looked at is we're starting at the current vehicle, so we're right here, and then this is our 0 point. And now, what do we want to do? How are we going to improve? And by how much are we going to go in the direction of one requirement or the other one? If it is nonlinear with respect to what the customer wants, I'm not sure. I'm not sure thought about it this way. I'd have to think about it more.
Okay. And finally, Christian asks, just in general, is this an early concept? I mean, does that happen in the early concept stage, or can you do this later in the architecture stage? Or does it apply at the detailed design stage where you're really facing the details of these trade-offs?
Yeah, it was probably more a conceptual stage where you do have a current solution and you're trying to figure out how can I modify that solution to better satisfy what the customer wants.
Kind of where to place the effort in the
Right.
next stages.
Yeah.
Interesting. I mean, as I reflect on this, I'm thinking, when I teach about how to handle trade-offs, I say, well, there's generally three approaches. There's prioritization, just decide which of the two performance dimensions is more important. And that puts you to one of the corners on your triangle thing.
Right.
And then the second approach is to compromise, to find some place in the middle. You give up a little bit of each, but not too much of either one. And the third is innovation, and that's where you kind of move the whole bowl up, and that's
Right.
So it's kind of interesting graphical way to think about these three different ways to address the trade-off. I mean, but it's not telling you what to do; it's just helping you visualize it. Okay, great.
That's true.
Thank
Yeah,
you, George.
and that was my difficulty, is not having enough data to try to be able to apply it and show whether it may work or not.
Okay, great. All right, let's turn to Carl and his paper around non-functional requirements and servitization. I'll start with the question I tried to articulate. As I read through the 6 issues you identified, it just seemed like, well, those are failures. I mean, that's a bad development process. I mean, it's not that we don't know how to do that right, but they aren't doing it right. And so is the recommendation to just, okay, well, do a better job, be more systematic about it? Or is that just, did you feel like that was just impossible given the organization and the culture in that place?
No, it's a good question, Stephen. And to elaborate on that, I think, because when you look at the functional domain and the functional requirements, what I saw in the case study was that they had no issues with the process on that side. So they were able to effectively both capture and then utilize and do the trade-off within the functional requirements. But it was challenging for them to, when it comes to non-functional, they didn't know how to fit those into the product development process that they had. So in that sense, I say it is more of how they could work more systematic with that side, that perspective, with the non-functional perspective, because the functional perspective, and this is one of the things I argue in the paper, that as a traditional pure product manufacturing firm, they have, for all the years they existed, they only had to care about what as getting a performance to a certain cost, basically, and then just deliver and sell their equipment. But when they start to servitize, they realize that, well, but wait a minute, there are other aspects, the more fussier and the soft side of the products and services that also matters to the customer. But our process is not, we don't know how to incorporate this in the process of how to manage these. So that was one of the, I was summarizing one of the main issues. And that caused them to, for instance, that they were often put on the back burner instead, and they continue to their old ways.
Yeah, it could be a matter of, and maybe this, I think, comes up also in Yevgeny's paper that we're going to talk about also. Services have requirements too. I mean, maybe they're not the same types of functional requirements we're used to dealing with the more tangible elements, but it doesn't mean they don't have requirements. So it just seems to me that it's a matter of kind of getting in the mindset of, well, if we're offering and delivering a service, that's how customers get value. We've got to understand their values, and so that we can get requirements for those service elements.
Yeah, exactly. So you can, for the services, let's say it's the same set of the finding the requirements, identifying, but if you are adding the services, and then you need to make sure that the product itself manage to complement or support these requirements, or that to have to adapt the product design. So I looked at the engineering from the engineering perspective. So when an engineer sits down and he or she wishes to make sure that the product enables a good flexibility or maintainability, they were not sure how to actually, okay, how do I make sure my design is flexible or maintainable?
Yeah.
That's where they sort of, the issues were found.
Yeah, it seems to me it's a matter of translating that into things that are more tangible. I mean, if the customer says, it's got to be affordable, like you still have to turn that into a tangible thing, like a cost requirement or an operational cost requirement thing. So, there's, how do you deal with anything that the customers say in their terms? You turn them into technical terms. Okay, I think this actually very strongly relates to what Yevgeny was wrestling with in the final paper. So I'm going to bring Yevgeny into this conversation. My conjecture is some of the organizations have a background in tangible products and they're turning them into PSS.
Yeah.
And others have a background in intangible services like IT services or whatever, or data and so forth. Do they have a different? Did you see any difference in the kind of challenges they faced? And the conjecture, the hypothesis is you're good at some things, but you're not good at everything until you get that experience.
Yeah. First of all, that's a great question that you have stated, because first of all, the enterprises were all different and had different backgrounds. And we had already beforehand conducting our study, we have assumed that there may be an implication and a connection between the experience and the sector and line of business with the issues and challenges. However, this study that we performed was not on a company level or business level, but on individual levels. So we were cautious to jump to conclusions during this study, but we followed up on this particular research question with our later work, which isn't published yet. However, we conducted further workshops with their enterprises. So we gathered the individuals in one setting to focus on the enterprise challenges, and our findings, just a brief spoiler, showed exactly issues in the opposite domain. So if a enterprise was in the past a manufacturer and producer of tangible goods, then most of the challenges were in the opposite domain. So basically service development, connection of product and service to a system. So adding to the question of Young, many enterprises were already providing basic services. So they had some kind of service development already integrated. So like maintenance or product customization. But the enterprises were struggling in connecting those areas mainly.
Yeah, I think, similar to what we're discussing with Carl, it's a partly matter of experience. And once after they've developed that system and they're supporting that system, they will know those requirements and they will understand them a lot better based on, their first experience with launch and customers and failures and feedback.
Exactly. Especially our enterprises being small and medium-sized ones, they're heavily specialized on one field. Bigger enterprises seem to be able to buy in this knowledge by through experts like engineering houses that have already experience, but small and medium-sized enterprises are lacking the basic know-how and what are smart PSS and what are the necessities to develop those.
They also have to know what they need.
Yeah.
And
I would like to make a comment.
Or buy it unless you know what you're looking for.
Steve, I would like to make a quick comment.
Yongsi.
Yeah, I think in both the Carl case and then the last paper case, I think that somehow the product is more. These companies seem to be more familiar with the the product side, not the service side. Okay, but the product related requirement is a functional requirement, and service related requirement is non-functional. That's completely kind of misleading issues. And also the smart PSS may be the with the smart product is also misleading issue. I mean, even though your product cannot be smart, okay, by developing smart services, you can actually make product services system smart. So I think the little bit of these two, the companies involved in these two studies are very unfamiliar with the service yet at this point. Okay, they're more comfortable with the product side, and this may be the reality of many SMEs. Then this is going to be some kind of a new mission for maybe academia to let them know more about services. Okay, so that's my comment.
That's an interesting perspective, and I do think you're right. It's largely a matter of experience, and once they get that experience, they'll know a whole lot more what to look for in those requirements. Okay, let's just take an opportunity to thank all the presenters and everyone for the questions and comments, the discussion today. I thought it was a really stimulating session related to complexity. Thank you, everyone. Our session has to conclude now, and look forward to the next one. Thank you all.
Thank you, everyone.
Thank you.
Thank you, everyone. Thank you, Stephen, for
Thank
hosting.
you.